Hello everyone, a very warm welcome to DMG chemistry classes, and in this video I am continuing my discussion on NMR spectroscopy, and in this chapter we will particularly focus upon proton magnetic resonance, that is PMR spectroscopy. And in my previous video we were discussing the theory and principle of NMR spectroscopy, and we will continue with that in this video also. So friends, in my previous video, I told you that just like that of electrons, the nuclear particles, protons and neutrons also spin about their own axis. And the nucleus will have some resultant spin if the protons and neutrons are not paired. And the resultant spin of the nucleus depends upon the number of protons and neutrons having parallel and anti-parallel spins. And I also told you that this resultant spin is called as nuclear spin quantum number, and the spinning nucleus possesses angular momentum, and the angular momentum depends upon the nuclear spin quantum number and calculated with the help of the formula, that is I prime, which is angular momentum, and it is equal to under root I into I plus 1 into h upon 2 pi units. And I also told you that a spinning charged particle or a charged particle which is spinning about its own axis generates a circular electric current, and which in turn produces a magnetic field. So we can say that a charged particle behave as a tiny bar magnet, or the nucleus of an atom behave as a tiny bar magnet, because nucleus contains charged particles, protons. Okay, so in this video I am going to discuss the nuclear spin states. So students, this angular momentum is a vector quantity and it will have both magnitude as well as direction. What this angular momentum vector cannot point in any arbitrary direction. It will point only in those directions in which its components are either integral or half integral. And its components will be integral if the value of I, that is nuclear spin quantum number, is integral. And the components will be half integral if the value of nuclear spin quantum number is half integral, because the value of angular momentum depends upon I, that is nuclear spin quantum number. Okay, तो हम कह सकते हैं कि जो एंगुलर मोमेंटम वेक्टर है वो किसी भी मनचाही डायरेक्शन में पॉइंट नहीं कर सकता. ये उन्हीं डायरेक्शन में पॉइंट करेगा जिन डायरेक्शन में इसके कंपोनेंट या तो इंटीग्रल होंगे या हाफ इंटीग्रल होंगे. हाफ इंटीग्रल कब होंगे? जब I की वैल्यूज हाफ इंटीग्रल होंगी, और इंटीग्रल तब होंगे जब I की वैल्यू इंटीग्रल होंगी. ओके, एंड द नंबर ऑफ कंपोनेंट्स विल बी इक्वल टू 2I plus 1, दैट इज नंबर ऑफ कंपोनेंट्स will be equal to 2I plus 1, where I is the nuclear spin quantum number and the components will be minus I plus 1, so on, then I minus 1, and the last component will be equal to plus I. So let us illustrate this with an example. So let us consider a nucleus which is having nuclear spin quantum number equal to 1. So we have a nucleus having this nuclear spin quantum number equal to 1. Then this nucleus will have 2I plus 1 component, means that is 2 into 1 plus 1, and it will be equal to 3. So this nucleus will have 3 components of angular momentum vector, and the components will be minus I, that is minus 1, then we will add 1 in it, then we have 0, then we will again add 1 in 0, and the last component will be plus I, that is plus 1. So in this way, the three components will be -1, 0 and +1. So we will go from -I to +I. -I will be the first component, +I will be the last component, and we will move from -I to +I by adding 1 in each component. Okay. And for a nucleus having I is equal to half, there will be two components, that is 2 into half plus 1 equal to 2, and the components will be minus half and plus half. Okay, that is minus I and plus I, or we can say that minus I then plus 1 equal to plus half. So these two are the components of the angular momentum vector when I is equal to half. Okay, and let us represent these components with the help of a diagram. Okay. In diagram we have a semicircle. Suppose the angular momentum vector is pointing in this direction, and the nucleus spin quantum number of the nucleus is 1, and this nucleus will have three components as I discussed, -1, 0 and +1. Okay, so this component is your +1, this component is your 0, and this component will be your -1. Likewise, for the nucleus having this nucleus spin quantum number equal to half, we have two components. Let us represent. So this is the direction of angular momentum vector, and I of the nucleus is half, and the two components will be represented like this. This is the first component and its value is plus half, and this is the second component and its value is minus half. Okay, and let us illustrate this rule with some more example. Suppose we have a nucleus with I equal to 2, and the number of components will be 2 into 2 plus 1 equal to 5, and the components are -2, then add 1, then we have -1, then -1 plus 1 equal to 0, then +1 and +2. So these are the components of angular momentum vector for the nucleus having I equal to 2. And for the nucleus having I equal to 3 or I equal to 3 by 2, I equal to 3 by 2, the number of components will be equal to 2 into 3 by 2 plus 1. Okay, and we have 4 components, and the components will be -3 by 2, then -3 by 2 plus 1. It will be equal to -1 by 2, then we have +1 by 2, and last component will be +3 by 2. So these are the 4 components of the angular momentum vector when I is equal to 3 by 2. Okay, and students, these components of the angular momentum vector are called as nuclear spin states. Okay, this means that the nucleus having I equal to 1, it will have 3 nuclear spin states. That is, it can spin in this direction. Okay, it can also spin in this direction or this direction. Likewise, a nucleus having I equal to half, it can spin in 2 allowed directions, and these directions are these, that is +half direction, and this is your -half. Okay, so these components of angular momentum vector are called as nuclear spin states or nuclear energy levels. What these nuclear spin states are degenerate. That is, these nuclear states have same energy. What when an external magnetic field is applied across the nucleus, then the degeneracy of these states are lifted. Okay, so let us explain it with an example, and here I am taking the example of hydrogen nucleus, the simplest nucleus which is magnetic or which behave as a magnet because it contains only one proton, and this nucleus have magnetic property. So let us explain it here, that how the degeneracy of these nuclear spin states is lifted in the presence of external magnetic field. Okay, so as I said, I am taking the example of your hydrogen nucleus, and hydrogen nucleus contains only one proton, and this hydrogen nucleus will behave as a magnet or tiny magnet, because as I said that charged particle behave as a tiny magnet. So here I have this hydrogen nucleus which is having one proton, and that proton is behaving as a magnet. Okay, so this is the north pole of the magnet and this is the south pole of the magnet. Now I have applied external magnetic field around this proton or this hydrogen nucleus. So here we have a magnet, and this is south and north pole of this magnet, and we have another magnet here, and these are its south and north poles. So this is external magnetic field which we have applied across this magnet, proton magnet I must say. So when this external magnetic field is applied, then definitely the north pole of this nucleus magnet or proton magnet will be attracted towards the south pole of the external magnet, and the south pole of this proton magnet will be attracted towards the north pole of the this external field magnet, and this proton or this proton magnet will be oriented with the direction of the magnetic field like this. Now this will be the direction of this proton magnet with south pole here and north pole here. Okay, now I can say that this proton or this proton magnet has aligned with the direction of the magnetic field, because the direction of the magnetic field is from south to north here, south to north here also, and the direction of the nucleus magnet is also from south to north. So when this is the case, then we say that this nucleus has aligned with the external magnetic field. And I have told you in my videos when I discussed chemical thermodynamics with you that whenever there is a force of attraction, there is stability, and whenever there is stability, there is fall in energy. So here attraction is there. This proton magnet is feeling attraction, that is its south pole is being attracted by the north pole of the external magnet, and its north pole is being attracted by the south pole of the external magnet. Okay, so there is force of attraction. This means that it will stabilize this proton magnet and its energy will fall or decrease. So let us represent it with the help of an energy diagram here. Okay, so along this direction we have energy, and this is the energy of the proton in the absence of the magnetic field. And as I said that when the external magnetic field is applied, its energy will fall or it will be stabilized. So its energy will decrease like this. So now this proton will be, or hydrogen nucleus will be in a lower energy state, and I am representing this state by +12. Okay. Now if I want to align this proton magnet against the external magnetic field, so to do this, I have to orient this proton magnet in this way. That is, its north pole will be here and its south pole will be here. Okay, that is, it will be aligned against the external field when its north pole is facing north pole of the external field, and the south pole is facing the south pole of the external magnetic field. And to do this, I have to apply some energy, because I have to align this proton magnet against the external field. I have to overcome the force of attraction which is already present here between the north and south pole of the proton magnet and the south pole of the external magnetic field, and the same force is also here. Okay, so when I have supplied energy and I have aligned this proton magnet against the external magnetic field, now the direction of its magnetic field is opposite to the direction of the external magnetic field. Okay, so when I have supplied energy, I have aligned it against the external magnetic field, then there will be repulsions, because now the north pole is facing north pole and the south pole is facing south pole, and repulsions are there, and repulsions never lead to stability, and repulsions brings instability. So the energy of the proton nucleus will increase or will be enhanced when it is aligned against the external magnetic field. So I am representing it here, that is, when it is aligned against to the external magnetic field, then its energy will be increased, and I am representing it here like this. Okay, then this proton will be said to will be in the higher energy state, and this state is represented by -12. Okay, so now I am coming back to the point that the nucleus which is having nucleus spin quantum number equal to half, it will have two nucleus spin states, that is 2I plus 1. So it will be two nucleus spin states, and spin states are -12 and +12, and these two spin states are degenerate. So here we were having two energy states, that is, one is your -12 plus and -12. Okay, and these were degenerate when there was no external magnetic field. But when we have applied external magnetic field, then this degeneracy is lifted and we are getting two spin states. Okay, one is of lower energy represented by half, and it is also called as alpha spin state. Okay, and another state is of higher energy, and it is represented by, or it is written, beta spin state. Okay, beta spin state, and in this way the degeneracy of these two nucleus spin states are lifted in the presence of external magnetic field. Now friends, this energy difference, okay, this energy difference between the two nucleus spin state depends upon the strength of external magnetic field. Means that if I increase the external magnetic field, then the energy difference between these two spin states will be increased, because the difference between these two energy states is given by the formula delta E is equal to gamma H into H naught upon 2 pi, where this gamma is called as gyromagnetic ratio, and it is a nuclear constant, and it is equal to the ratio of the angular momentum of the nucleus to the magnetic moment of the nucleus. So it is a nuclear constant called as gyromagnetic constant or gyromagnetic ratio, where this H is the Planck's constant and H naught is the externally applied or the strength of the externally applied magnetic field. Okay, so you can see from this formula that the energy difference between these two states is directly proportional to the strength of the external magnetic field. Okay, so the energy difference will increase as the strength of external magnetic field will increase. And we can also explain it here, because as the strength of the external magnetic field is increased, then the attraction between the south pole and the north pole of external magnet and the proton magnet will be increased. Okay, and when the attraction is increased, this means that there will be more stability and there will be more fall in energy. So when we increase the external strength of the external magnetic field, then the force of attraction between the north and south poles of external magnetic field and the proton magnet increases, stability increases, and its energy will fall further. And likewise, when the proton magnet is aligned against to the external magnetic field, then we will have more repulsions in this state. So there will be more repulsions here. Then it is aligned against the external magnetic field. So the energy of the that higher energy state will be enhanced further. Okay, so I can represent here diagrammatically that if delta E1 is the energy difference between these two spin states, okay, when the external magnetic field is H naught, and this energy difference will be increased further if I increase the external magnetic field. Suppose I have increased the external magnetic field to a new value H naught prime, then the energy of this alpha spin state will be decreased further. Okay, and that of your beta spin state will increase like this. And here the energy gap between these two states, I am representing it by delta E2, and here the externally applied magnetic field is H naught prime. Okay, and this your H naught prime is having large value as compared to H naught. So the energy difference, that is the delta E2, will be more than delta E1. Okay, so friends, like this I have explained here that as the strength of external magnetic field increases, the energy difference between the nuclear spin states enhances further. Okay, now I am coming to the principle of NMR spectroscopy. This is going to be very interesting, so keep watching this video till very end. Now, when we have applied external magnetic field, then the nuclear spin states are created or nuclear energy levels are created. Okay, and the proton magnet or the nucleus, it will preferably occupy the lowest energy state. So the proton or the nucleus, it will occupy the lowest energy state. Now what I want to, and here it is aligned with the direction of the magnetic field. Now as I said, and if I want to align this nucleus against the external magnetic field, then I have to supply some energy. So here I want to excite this proton nucleus, proton magnet, from this your lower energy state, that is alpha spin state, to the beta spin state. So I have to apply some energy. And in NMR spectroscopy, this energy is supplied by electromagnetic radiations. And in this spectroscopy, radio waves are used. And what we will do here, we will irradiate this proton. Okay, we will irradiate this proton with the radio waves of varying frequency। मतलब ये कि हम इस प्रोटॉन के ऊपर अलग अलग फ्रीक्वेंसी की रेडियो वेव्स डालते जाएंगे, और when the energy of the radio wave or the frequency of the radio wave matches with this energy difference, that is energy of the radio, when the energy of the radio wave becomes equal to this energy difference, then that radio wave or radio frequency will be absorbed and the proton will be excited from the lower nuclear energy level to the higher nuclear energy level, or from alpha spin state to beta spin state, and spin flip will take place. Okay, so friends, when the energy of the radio frequency becomes equal to this energy difference, then the nucleus is said to be in resonance with the radio frequency or radio wave. Okay, that's why we have this word resonance in NMR spectroscopy, because the full form of this spectroscopy is nuclear magnetic resonance. And we can easily calculate the frequency which will be absorbed corresponding to this energy gap with the help of the formula which we have discussed earlier. That is, the energy gap, that is delta E, is equal to gamma h upon 2 pi into h naught, where gamma is the gyromagnetic ratio and h naught is the strength of externally applied magnetic field. And we also know that delta E is equal to h nu. Okay, so now we will substitute the value of delta E here, then we will have this h nu equal to gamma h into h naught upon 2 pi, and the Planck's constant will be cancelled and nu will be equal to gamma h naught upon 2 pi. So with the help of this formula we can calculate the radio frequency which will be absorbed when the strength of externally applied magnetic field is h naught. And for the proton, the value of gyromagnetic ratio gamma is equal to 26,750. So we can calculate the value of radio frequency corresponding to the magnetic field, that is the strength of the magnetic field is equal to 14,092 Gauss. Okay, and this is the strength of external magnetic field. Now we will calculate the radio frequency which will be absorbed when this is the strength of external magnetic field with the help of this formula. And after calculation, the value of frequency comes out to be 60 megahertz. Okay, this means that when the strength of external magnetic field will be 14,092 Gauss, then the radio frequency absorbed will be equal to 60 megahertz. Okay, so this is the principle of NMR spectroscopy, and in my next video I am going to discuss the NMR spectrum and origin of the signal in NMR spectrum, and which is going to be very interesting. So keep watching my videos, also like and share my videos, and don't forget to subscribe my channel. Thank you very much.